oil pressure is sensed at the outlet of the oil pressure pump. Normally, the oil pressure of an engine is maintained constant by an oil pressure relief valve. There are, however, situations which may affect the engine or the oil to the extent that it is beyond the ability of the pressure relief valve to maintain the oil pressure within the prescribed limits. It's at these times that the oil pressure gauge, if it's used in conjunction with the oil temperature gauge, can indicate to the pilot the best course of action to retrieve the situation. The manifold absolute pressure gauge of a piston engine uses two bellows to measure both ambient atmospheric pressure and the pressure in the inlet manifold. Note that this gauge measures absolute pressure and is calibrated in inches of mercury. When the engine is running, this gauge may indicate less than atmospheric pressure. Earlier versions of this gauge were calibrated to read boost in pounds per square inch, and called boost pressure gauges. When the engine is not running, both types of gauge, the manifold absolute pressure gauge and the boost gauge, will read ambient atmospheric pressure. While the aircraft is stationary on the ground, this particular indication is called static boost. A fuel pressure gauge may be fitted to fuel injection fuel systems and can be used to indicate metered fuel pressure. In some cases, by calibrating it in a suitable manner, the fuel pressure gauge can enable the pilot to adjust the air-fuel mixture to suit the aircraft's altitude and the engine power setting. The measurement of the quantity of fuel in the tanks of an aircraft fuel system is an essential requirement. The simplest form of volume indication is a float system. Early aircraft had a float which sat on top of the surface of the fuel. Attached to the float was a piece of wire that protruded out of the top of the fuel tank. As the fuel level reduced, so the wire disappeared from view. There have been many variations of this system. On light aircraft, the most common of these uses a float which moves to position a wiper on a variable resistor. This in turn alters the current flowing to an indicator, moving a pointer over a scale calibrated in volume. The disadvantage of this system is that the indication is not linear, and there is no provision for making adjustments for system accuracy. The gauge is set to be accurate at the low and empty positions. The system is also subject to errors whenever the aircraft maneuvers and the attitude changes. As well as the quantity of fuel measured, the rate of fuel flow can be shown. The fuel flow meter can display volume flow or mass flow. A simple flow meter can be an adaptation of a pressure gauge. This system is used on many light aircraft piston engine fuel injection systems. The measurement of engine speed is of vital importance, since together with other parameters, accurate control and monitoring of the engine can be achieved. On piston engines, it's crankshaft speed that is measured. The RPM indicator is called a tachometer, or tacho for short. The basic method of measuring engine rotational speed on piston engines is the mechanical magnetic tachometer. The mechanical tachometer consists of a flexible drive shaft and the tacho indicator. One end of the flexible drive shaft is connected to the tacho indicator in the cockpit. The other end goes to the accessory drive casing on the engine, where it's driven through gears from the crankshaft. The input drive causes a magnet to rotate. The magnet rotates inside a copper or aluminium drag cup. This induces eddy currents in the aluminium drag cup. Eddy currents are caused by the magnetic field of the moving magnet, acting on the electrons of any metal in the vicinity of the magnet. The eddy currents themselves generate a magnetic field, which interacts with the magnetic field of the magnet. This interaction causes a torque, or turning moment, which is established to turn the drag cup in the same direction as the permanent magnet. A shaft extends from the drag cup and is connected to a pointer. The turning motion of the pointer is against the tension of a hairspring, which controls the drag cup position and hence the position of the pointer. The flexible drive is driven at reduced speed, but true speed will be shown on the indicator. The indicator incorporates compensation devices for changes in temperature. Left-click on the blue slider button situated below the tacho generator diagram with your mouse, and move it right and left to see how the device works. Notice how the spring restricts the drag cup as it turns the pointer.